So let's take a continuous function again. So we let f be a continuous function. On a type 2 region. Let's call it B. Given by the following set. So it's the set of all points. X, Y in the plane. For which X is greater than or equal to H1 of Y. But less than or equal to H2 of Y. All right. So the region is something like this. Well, of course, we have to specify the range of Y as well. So let's say Y is between C and D. Okay. In other words, there is an interval, CB, on the y-axis. So, looking in this direction. Then we are going to have a function defined on the interval C. And then another function, which is more to the right of the first curve. So the graph of this function can be written as x equal to h1 of y. So if you look from this direction, x is a function of y. And this one is x equal to h2 of y. And this time we are going to look at the integral, the double integral. On D, this is the region D. The double integral on the region D of the function with respect to A is given by the following. So we integrate with respect to x first. And then I am going to integrate with respect to y. All right. And the way to do it is to fix a y here. In the interval from C to D. Okay. And then I am going to let y go from C to D. If you do this, then you can see that x actually goes from this point to that point. Okay. And we are going to let all these cross section of the region D. In other words, we are going to let all these level lines go from the bottom of the region D to the top. Then you would cover the whole region D. So when you fix a y from C to D, the corresponding x would go from this point to this point, which is h1 of x to h2 of x. No, h1 of y, sorry. To h2 of y. So when you integrate with respect to x from h1 of y to h2 of y, you will get a function of y. And then you are going to integrate this function of y with respect to y from c to d. Okay? So we have observed that there are actually two ways to compute this double integral of the function f on the region D with respect to the area. Okay. Last Friday, I gave you the formula for type 1 region. And today is the formula for this type 2 region. Any question? Now, let's look at an example. So let's try to find the volume. Of a solid in 3-dimensional space. Now, let's try to look at this solid. It's not that good to use S for solid and S for surface. But both begin with the letter S. So let's stick to it. So we are going to find the volume of the solid S carved out by the following data. So the solid is bounded by the following planes. So this is one of them. And then the XY plane. the YZ plane. And finally, the XZ plane or ZX plane, whatever you prefer to call it. All right. That's the question. So in order to get more insight into this question, let's draw a figure first. So here is the figure. In the X, Y, Z space, now, what is the plane given by X plus Y plus Z equal 1? You don't have to write the equation down again, but I need it for explanation. That's it. Now, what does the plane look like? Well, the way to draw it is like this. First of all, I put X equal to 0. Then you are on the YZ plane. You are on this plane. Okay? So I get Y plus Z equal 1, which is a line, right? Which is a line. So when Y is equal to 1, Z is equal to 1. No, just a minute. When X is equal to 0, and then I want to draw this. So I put Z, I put Y equal to 0. So I cannot go that far away. So it has to be here. And Z has to be equal to 1. Looking at Y plus Z equal to 1 again, when Z is equal to 0. And you are here. And then Y has to be equal to 1. Okay? So I get a line. Now I am going to put Y equal to 0. I have x plus z equal to 1. So when I put y equal to 0, I have this xz plane. And then doing exactly the same thing as this line, we are going to get a line going like that. And then finally, on the xy plane, z is equal to 0. We get the plane, a portion of the plane, which is a triangle. And then I want to look at the side. Capital S, bounded by this plane, the triangle, and the xy plane, yz plane, and xz plane. So what is S? So S is what people usually call a tetrahedron. So it's a tetrahedron. Now we are interested in the volume of this tetrahedron. Now, how to do it? Now, in order to do it, we are going to do it in the following way. So it can be calculated as follows. I am going to calculate the volume by a double integral. Okay. We don't do it in arbitrary ways, but we want to do it by a double integral. All right? Because this is the part of the course on double integrals. All right. How to do it? To calculate this volume using a double integral, then we have to know what the double integral is. For a double integral, we need a function defined on our origin. Now, can we visualize this inclination plane, the triangle, as the graph of a function? Can anybody tell me how to visualize this plane here?
When you view it from the z-axis, like when you look at the x and y.
Let me finish first. Can anybody tell me how to visualize this as the graph of a function? Okay. To be more precise, what is the function? Okay. Now, can you tell me what the function is?
Y is equal to 1 minus x.
Y is equal to 1 minus x.
Yeah.
I am talking about this inclination plane. What is the graph of a function in three-dimensional space? You have a region here. You have a surface here. That's why I said it's not good to use the capital letter S for both things. I'm not going to denote this by anything. This is good. And usually, this is the graph of a function of what form? Z equal f of x, y. So assuming that this is the surface S, then how can you get the function? This is f of x1. So, anybody? Well, what is this plane? This plane here is x plus y plus z. Equal 1. So, what are you going to do in order to get z as a function of x and y? What is z equal to?
Move the x and y to the right side, so it's 1 minus x minus y.
Now you got it. Okay. All right. So we let z be the function, which is 1 minus x minus y. And certainly it's a very nice function. It's a continuous function in particular. It's in fact a polynomial in x and y, or a linear function in x and y. So we have the function. And the next thing we need to have is a region over which you are going to integrate the function. Now, what is the region? The region B.
Let the triangle on the XY axis.
For on the XY axis.
Yeah, the triangle
But
bottom. That is our region D.
Wow. You are going to look at the triangle.
Yeah.
On the XY plane.
Yes.
Okay. So where B is the triangle. Well, the domain is usually the projection of the surface on the XY plane. So when you look from above, I have to eliminate the noise first. Okay. All right. So this D here is the triangle. With the following vertices. I remember once when I taught calculus, I forgot which year it was. And then in the final exam, okay, well, in the past, I think you still remember that you have to write the exam in a big room for a fixed number of hours. And I usually did not allow any references. They asked me, what is the meaning of this word? I don't know what I did. I cannot remember. Now, the vertices are actually the corners of the triangle. So it's 0, 0. And then 1, 0. And finally, not 1, 0, 1, 0 is this one. And this is 0, 1. No. 0, 0, and then 0, 1. Okay. So let me try to draw the region. And the region is just a triangle in the XY plane. So let me put this one up. And we are going to have the triangle given like this. So it's this triangle here. This is the origin. And we have these 2 points. Now, actually, you can think of this region D as a type 1 region or a type 2 region. When you look at it as a type 1 region, you look at it in this direction, right? And when you look at it as a type 2 region, you look at it from this direction. So it's both. So you can choose either one you like. But let's just take it. Let's try to pick the type 2 region. Because in the notes, I did it by looking at this region as a type 1 region. Is it? Yeah. So I am going to look at it from this left to the right. Okay. And the volume. Of the solid S, this tetrahedron, can be computed in the following way. Is the double integral quantity of f at xy, which is 1 minus x minus y. With respect to area. So we need to compute this by looking at this region as a type 2 region. So y is between 0 and 1. This is 1. So we fix a value y on the y-axis. And then you have to look at the corresponding range for x. So what is the range for x when y is here? Anybody?
0 to x bracket y,
0 to x,
bracket y. X value when y is y.
y is already fixed. So it should be a function of y,
1 minus y.
1 minus y, right? So it's 1 minus y. No. Is it correct?
In the notes, it says 1 minus x.
No, you fix y. And then what is x? In other words, what is x? So x is here. Okay? So it's correct. Okay? So now, is this okay for everybody? Or I have to explain a little bit more. The x corresponding to this is 0. You go from 0 to this point. And this point is x. And then we know that x plus y is equal to 1 because of this line. So x is actually given by the following thing. What is it? So you have to look at the equation. Where is the equation? Okay.
When y is 0, x is 1.
Yeah. Now, we put x equal to 0 because we are on the xy value. So y actually goes from here to there. So is it correct?
No, x moves from left to right. Y moves from to 1, then x moves to 1 from 1 to 0.
we have to look at x. I think it's better to write down more details. Right? This h1 of y is this curve, which is always equal to 0. And then I have x equal to h2 of y, which is to the right of this line. And then from here, you see that x can go up to only 1 minus 1. Okay? All right. This is the simplest situation to figure out the upper limit and the lower limit for a double integral. And then later on, when we come to polar coordinates, it gets more complicated. And for triple integrals, it's even messier. All right. But right now, it's not that. This is why it's good to look at it from a perspective different from the notes. So I have the following integral. Now, this time I am going to integrate with respect to x first, and then y. And then for this outer integral, the range usually consists of an interval. And in our case, is from 0 to 1. And then once you fix a y, x is from 0 to 1 minus 1. All right? So this is the integral we need to compute. Let me call this volume V. I don't want to write the same word again and again. Therefore, the volume V is given by the following. So it's the integral from 0 to 1. Of this integral as a function of y. So let's integrate with respect to x. So when you integrate 1, you get x. When you integrate x, you get x squared over 2. And then when you integrate y with respect to x, what do you get?
X times Y.
X times y. All right, because y is held fixed. So it's minus x times y. And then you have to evaluate the integral or the function at the limits. I think it's better to write it as x equals 0, x equal 1 minus y. Okay, and then dy. In other words, we integrate with respect to x first and then y. So is the integral from 0 to 1 of 1 minus y minus 1 minus y squared over 2 and finally we have this y times 1 minus y. dy. Well, unfortunately, time is up, but I believe that you can integrate this function yourself. So I stop here. Okay. Or you want me to finish it?
So pretty much we have to integrate the inside first and then we integrate the outside, right?
That's what I said, yeah. But do you want me to finish it anyway? But it's already quite over time.
I think the answer should be the same.
I think it's pretty straightforward from here.
Yeah, it's very straightforward. Yeah. You either make a substitution or you just expand and then you can do it. Okay. Well,
Thank
it has to be the same. It has to be the same value. Okay, the same value when you look at the region as a type 1 region. Okay. I don't want to be too much over time.
Thank you.
You're welcome. So, any further questions? So, if not, see you either tomorrow or Wednesday.